Now we're going to jump into some further concepts that relate to the scientific method. Now there are two concepts that we want to talk about on this screen. The first is something referred to as empirical. So a thing is empirical if it exists in the world and can be observed through the senses. So by way of example, the human heart is empirical, however love is not empirical. So the heart can be seen and felt as an object, its pumping action can be observed in surgery, and its activity can be heard and felt at other times, constantly. It's required to keep us alive. Love does not meet any of these requirements to be an empirical entity. So there we provided an example of an empirical concept, such as the heart, versus one that is not empirical, which is love. The second important distinction or term to get around is the concept of a scientific law. A scientific law is a description of a fact that is completely accepted in the scientific community. Scientific laws state something in the natural world happens, but they don't necessarily explain how or why. The law of gravity is an example of a scientific law. It explains what happens, but not how or why. Now, to give you a bit of auditory respite, I'm going to play a video that explains or extends upon this concept of what a scientific law is and how it differs from a scientific theory.
Theory versus scientific law. It is important to understand the similarities and differences between a scientific theory and a scientific law. Both scientific theories and scientific laws describe something that has been observed in nature. They both require many observations and experiments, and they both must be accepted by the majority of the scientific community. However, scientific theories are not laws, and they are not treated the same as laws. Unlike a theory, where evidence changes, a law will never change. In science, a theory is a widely accepted explanation supported by abundant scientific evidence. Theories are not just ideas or guesses about how something works, and theories are not just opinions about a concept. For science to prove a theory, scientists must conduct extensive tests and experiments. A theory must be supported by tremendous amounts of scientific evidence, and it must go through peer review and retesting. Even if a theory is proven, it is subject to change in the light of new evidence. This is the best way for science to evolve and change. In this way, scientists can use theories to build upon the evidence and ideas of other great minds. One good example of a theory that has evolved over time is Newtonian mechanics, first theorized by Isaac Newton in the 1600s. This theory explained the movement of objects, both on Earth and in space. Using Isaac Newton's work, Albert Einstein perfected the theory, renaming it the theory of special relativity. Einstein's new theory put a twist on the Newtonian theory, allowing us to measure objects in reference to space and time. Einstein even upgraded his special relativity theory to a more current version that we use today, the theory of general relativity. Scientific laws are different from scientific theories. A scientific law is a description of a fact that is completely accepted in the scientific community. A scientific law does not change, and if it is refuted, not only does the law become false, but all science that was based on that law also becomes false. Laws state that something in the natural world happens, but they do not necessarily explain how or why. The law of gravity, for instance, states that all objects have a force of attraction for each other. This law explains what happens, but not how it works or why. Theories attempt to explain the how and why. When trying to decide if something is a scientific law or scientific theory, ask yourself this question: does it explain what happens, or does it explain how and why something happens? If it explains what happens, you are talking about a law. If it explains how or why something happens, you are talking about a theory.
Okay, so now we're going to speak again and in a bit more detail about the scientific method. So the aim of the scientific method overall, if I had to summarize it, is to remove any bias from the researcher. So the scientific method is used to critically analyze information. The goal is to uncover laws that govern empirical aspects of the world. So what we just spoke about earlier, what was covered in that video just prior. The scientific method is objective. It's meant to be unbiased, and it's about unbiased observation or recording of phenomena. The development of theories about cause and effect relationships is also quite integral to the scientific method. And again, a key criteria of the scientific method is that we can derive a hypothesis that can be falsified or proven wrong. Okay, so there's a slide here that reads planning a research study. And the purpose of this slide is to demonstrate that there are many stages involved in planning a scientific research study. It's quite an intensive and laborious process. And I will speak more to this or about this in our lecture next week about the process of designing research study or a qualitative research study, which is my current PhD. But in brief, there are several steps to this process. Firstly, you have to formulate the question. You have to identify a question that is worth answering and demonstrate why it enables a unique and significant contribution to scientific knowledge. So you need to justify the question, and you need to locate the question with relevance to previous or extant research. So what has been asked before, what answers have been found, and what are some knowledge gaps? You then need to refine and formulate the aims. So what is the purpose or aim of your research? What strategies will be used? So this is a question about research methods in a way. And what are the ethical considerations of those particular research methods? And resources have to be realistically available. Okay, so now we're going to talk about two research strategies very briefly. The first is survey research design. In survey research, the researcher must define the population of interest, then selects the cases to be studied, and then observes them, which generates the data. So in survey research design, there is no intended intervention by the researcher. Rather, the aim is to observe and not to influence subjects, which may change the data. So an example of a survey research design. So I am part of the Transmedical Research Group, and when COVID happened, the Transmedical Research Group was really interested in, monitoring or mapping the effects of COVID on trans and gender diverse people's experiences of health and well-being. So what they did is they identified a population, which is trans and gender diverse adults within Australia. They then created an online survey. So this online survey asked questions across a broad range of health and well-being indices or outcomes. So they asked questions about, for instance, have you had any gender-affirming surgery cancelled in this time? If so, what was the impact on you? So they sampled trans and gender diverse adults from the Australian population. They created a link to the study, and then they circulated that across several social media platforms. They then collected the data from people about their unique experiences of COVID. So this data is observation data. So they weren't trying to change any of the conditions of the participants. Rather, they were simply trying to map the experiences of trans and gender diverse adults during this time. So that's survey research.